Hi, everybody. Welcome back. Today, we're going to continue the discussion on the normal distribution. We're going to look at various types of problems that can be solved using the normal distribution, in addition to the probability questions that we introduced last lecture. Let's recap what we already know about the normal distribution. The normal distribution is a continuous probability distribution that models many real-life data patterns. It has this characteristic bell-shaped. We call it the bell curve because it looks like a bell. We talked about how to solve probability questions using the normal distribution, and we do that by identifying an area that corresponds to the event. So the probability of an event happening, let's say the probability between two continuous data values A and B, the probability of that happening is the area underneath the bell curve between A and B. And this shaded in area is the answer to the probability question. It's a number between 0 and 1, and you figure it out by using normal CDF. Normal CDF is our calculator function that helps us find the area corresponding to a shaded in portion of the bell curve, and it's always a value between 0 and 1. It takes four numbers. The first of the four is called the lower bound. That's always the leftmost bound of your shaded area. And then the other number is the upper bound. That is the rightmost bound of your shaded area. So we have lower and upper. And we have two more numbers. We have the mean and the standard deviation of the distribution, and you cannot do any problems without those two values. You can't use any normal CDF, or you can't use normal CDF to solve a problem unless you have the mean and the standard deviation of a distribution. Okay, let's review what we know about z-scores, because we're going to start seeing some questions in a moment that involve z-scores, and I want to just refresh what we know about this topic. A z-score represents how many standard deviations a data point is from the mean. We have this formula, x minus mu divided by sigma, and it helps us calculate the z-score. How do z-scores relate to the normal distribution? Well, z-scores help us standardize data to compare it across different normal distributions. A z-score of 0 means the value is exactly at the mean, and that's right in the center of the distribution. And to the right of that z-score of 0, we have the positive z-scores. These represent numbers that are above the mean. And on the left, we have the negative z-scores, which represent numbers which are below the mean. And just to go back to the idea of standardizing data to compare it across different normal distributions, there was a homework question like this that asked you to look at two different distributions. One, a normally distributed distribution that talked about grip strength, and another normally distributed group that measured VO2 max. Two normal distributions, and you were to calculate two different z-scores. When you compare the z-score of one distribution with the z-score of the other distribution, you were able to see which z-score was more outstanding, which stood out more, and that was the one with the bigger z-score. And you found the z-score using the z-score formula. It's a measure of how many standard deviations above or below the mean. And generally, our z-scores fall between -3 and +3. On occasion, they will be greater than +3 and less than -3, but this is rare. It occurs less than 0.3% of the time. Okay, so that's what we know already about z-scores. I have two bell curves here. One measures systolic blood pressure, and you can see the values on the horizontal axis look like blood pressures. And the other one measures just z-scores in general, and you see these numbers on the horizontal axis are z-scores. For the systolic blood pressure, I have a mean and I have a standard deviation given. And for the z-scores, the mean, you can consider the mean z-score to be 0. Okay, so if we think of z-scores as rescaling the data set, the mean therefore becomes 0. So imagine that this 120, when measured as systolic blood pressure, is actually a z of 0 when rescaled to look like z-scores. Now, what else is rescaled? The standard deviation. So let's take a look at the standard deviation for blood pressures is the distance from one blood pressure to the next one, as identified by these numbers here. And the difference is 15. Okay, if we keep adding 15, we can get subsequent blood pressures. And if we subtract 15, we'll get subsequent blood pressures on the left. Now, what happens on the z-score side? To get from one z-score to the next, you're not adding 15. What we're doing here is adding 1, right? We're adding 1 each time. And if you think about what's happening on the left, you're subtracting 1 each time. So we're going to say our mean for the z-score is 0, and the standard deviation, that number that we keep adding or subtracting to the left or the right, is 1. Okay, we're going to say that, oh, look, I just wrote over. Let me get rid of that. Okay, our mean of 0 and our standard deviation of 1. So no matter what the original scale of the data was, so in this case, we're dealing with blood pressure, but it could be other things that we're measuring, no matter what it is. When we convert to z-scores or rescale our distribution to z-scores, the standard deviation of the distribution is 1, and the mean is 0. Knowing that, it enables us to use normal CDF with z-scores now. So let me show you an example. A nurse in the ER is monitoring a patient's heart rate. For adults, resting heart rates are normally distributed. Okay, so that's an important piece of information. Resting heart rates are normally distributed. What is the probability that an adult patient's z-score for resting heart rate is greater than 0.5? So we're asked about a z-score being greater than 0.5. Notice that we don't have a given mean and standard deviation for this distribution, but we know the mean and the standard deviation for the distribution simply because this is given to us as a z-score. The heart rate is given to us as a z-score of 0.5. So for that reason, we know that the center is 0, and we know that the standard deviation is 1. Okay, and to understand why it's 1 again, go back to the previous slide. We add 1 each time to get the next z-score on the right, and we subtract 1 each time to get the z-scores on the left. The standard deviation is 1. So now if we're asked to find a probability using the normal distribution, we need to use normal CDF. That's our tool for figuring out probability with the normal distribution. So let's shade in the area in question. The z-score of 0.5 is located halfway between z equals 0 right here and z equal 1, a little to its right. So mark up the let's mark up the horizontal axis with z-scores. Okay, let's take note of where z equals 0.5. Where does z equal 0.5? So it's going to be right here between 0 and 1. We're going to make a vertical line that hits the curve. Okay, make a vertical line at that 0.5 and touch the curve at the top, and then take note of what the question is asking you for. It's asking you to find the probability that the z-score is greater than 0.5. So greater than means to the right. We're going to continue this shaded area from the vertical line that we just created all the way to the right. And we recognize that all the way to the right from our discussion last class is positive infinity. And we use E99 on our calculators for representing positive infinity. So that's what we're going to put on our calculator. We have our mean and standard deviation here. We have our lower bound and we have our upper bound. Okay, so I will, let me take you to the calculator right now and we could do this together and then I'll come back to the slideshow. Okay, here we are. So let's go to normal CDF. We press second and then the DISTR, which is above the VARS key. We go down to number 2, normal CDF. And for our lower, remember this is the z-score 0.5. This is the left bound of our picture. And our upper, mine is automatically put in place there, E99, but let me show you how you would put it in place if it wasn't there. The E, we did this last time, is above the comma. Second, and the comma button will bring the E up for you, and then 99. So that's considered to work as if it's positive infinity. It's just a very large number. And when our calculations are done internally in the calculator, it arrives at an answer as if it were positive infinity. Mu is 0, standard deviation is 1. And let's paste this. Okay, and our answer, 0.3085. I'll take all these probabilities to 4 decimal places, so 0.3085 or 30.85%. Okay, so the slideshow has all this information as well. 0.3085, 30.85%. So realize in this problem, we were not provided directly with the mean and standard deviation, but because the problem uses z-scores and not raw data values, the mean is automatically considered to be 0 and the standard deviation is considered to be 1. Let's interpret this. The probability that an adult patient's z-score for resting heart rate is greater than 0.5 is 30.85%. So let's take a look at another example with z-scores. A hospital is tracking recovery times for patients undergoing a specific physical therapy program. Recovery times in weeks are normally distributed. So we're dealing with the normal distribution and we're going to be using z-scores. Z-scores are used to standardize recovery times across patients. So our data is not going to be provided in weeks. It's going to be provided as z-scores. What's the probability that a randomly selected patient's z-score is between negative 0.2 and positive 0.2? So we are asked for probability, which is the key to using normal CDF. Normal CDF is our tool for solving probability questions in the normal distribution. We have a lower and upper bound, but they are z-scores, so we know the mean and standard deviation are 0 and 1. Okay, so this will be our lower and our upper. Let's write that down. Let's put our z-scores on the horizontal axis and roughly identify where negative 0.2 is and where positive 0.2 is. So a little bit to the left of 0, a little bit to the right of 0. Make your vertical line for each arrow there. Shade in the area in between. That's the probability. The area is the probability. So our lower number, lower bound, negative 0.2, upper bound, positive 0.2, mean and standard deviation are 0 and 1. So we go back to normal CDF and use that information. Let's make sure, you know what, I'm going to go do this with you also. We're going to make sure we use the negative key and not the minus sign. So just a second, let me get there. Okay, let's do second distribution, normal CDF number 2. We're going to make sure that we use the negative sign to the left of enter, negative 0.2. Upper will be positive 0.2. Mean and standard deviation, let's leave that at 0 and 1 and paste. Okay, so our answer here, 0.1585 or 15.85%. Okay, so here we are on the slideshow. If you want to review, you have access to these slides. And let's interpret this. The probability that a patient's z-score for recovery time is between negative 0.2 and positive 0.2 is 15.85%. Okay. I have one more example for z-scores, just to make sure you get the hang of this. An endocrinologist is studying fasting blood glucose levels in adults. Fasting glucose levels are normally distributed. Z-scores are calculated to identify extreme cases. So we know that we're dealing with the normal distribution, and we also know that we're working with z-scores here. What is the probability? So use normal CDF to answer a probability question that a patient's z-score is less than negative 2.5, sorry, negative 2.5. So less than a z-score is going to indicate that the area in question is to the left of that z-score. So let's make our bell curve with our z-scores on the horizontal axis and locate the z-score in question. It's negative 2.5. So if we find negative 2.5, it's around here, halfway between negative 2 and negative 3. Your picture doesn't have to be perfect. You're going to make your vertical line and recognize that if the problem is asking us for probability less than a value, it means it's the area to the left of that value. Less than to the left. So we're going to shade in the area to the left, and we're going to use normal CDF to figure out exactly what that area is. So here you go, a normal CDF, second distribution, number 2, normal CDF. Your lower is going to be negative infinity, and your upper is negative 2.5. Let me go back to the picture for a second to make sure that you see that. So in this picture, when I shade in this area, the bounds, the lower and upper bounds are always the left. That is always the lower. And the right is always the upper. Okay, so what we have to do on our calculator when we run normal CDF is make sure that our left, our lower, is identified as negative infinity, and the right, our upper, is negative 2.5. So that's why for our lower, we're going to put in negative E99 for negative infinity. For the upper, negative 2.5. Mean and standard deviation, 0 and 1 like before, and paste. And this is a rather small probability, 0.0062 or 0.62%. Okay, not too big. And to interpret it, we're going to say that the probability that a patient's z-score for fasting glucose levels is less than negative 2.5 is 0.62%. Okay, 0.62%. So our picture, it wasn't exactly spot on. It didn't look to me exactly like 0.62% really. It looked a little bit bigger, the shaded area, but that doesn't matter so much. You're not being graded on the accuracy of the picture. You're being graded on the accuracy of your final answer. So the picture is there to help make sure that you put the right numbers into your calculator and to recognize a reasonable answer. So I can see, let's go back to the picture. Okay, I can see from my picture here that a reasonable answer is probably going to be on the smaller range as far as probability. An unreasonable answer, something that is larger than 50% would be very unreasonable. Because if you look at this and you try to guess approximately what it is, I don't think we should guess anything more than 40% if we're doing this freehand in a notebook. You shouldn't be when the calculator gives you an answer, you should have an expectation of what a reasonable answer should be. So while we do rely on the calculator for a lot of our answers, we do have to understand why or why not it's a reasonable answer. And make sure that we're correct when we do this on an assessment. So these scenarios provide realistic context calculating probabilities using z-scores and show how these calculations apply in medical settings. So those were 3 examples on your homework. You have a couple more to do. And this is just another way that the normal distribution is going to be presented to you in solving or in solving problems. So it can get a little complicated when you see all these different types of phrasing. That is all solved in a very similar way, but with practice, you'll get the hang of this. So I want to take us to a different way problems could be phrased, and that's using the term proportion instead of the term probability. So questions that ask you to calculate probability can also be phrased to ask for a proportion, but they're solved in the same way. For example, IQ scores are normally distributed with a mean of 100 and a standard deviation of 15. I could ask you the question, what is the probability that a randomly generated person, I'm sorry, randomly selected, thinking about some other topic in another course. What is the probability that a randomly selected person has an IQ score greater than 130? So you can solve that problem with normal CDF, where your lower is 130, your upper is positive infinity, your mean is 100, and your standard deviation is 15. But the same question could be phrased like this. What is the proportion of people with IQ scores greater than 130? So they mean the same thing. They're asking you out of your population, what's the proportion of people with IQ scores greater than 130? It's the same thing as asking what's the probability of randomly selecting a person from the population with an IQ score greater than 130. They both mean the same thing. So you would solve that in the same way. So let's actually solve this problem. Let's put our IQ scores on the horizontal. 100 is the mean. If the standard deviation is 15, we could approximately create a horizontal axis with 115, then 130, then 145, and then subtracting 15, we have 85, 70, and 55. And then if we locate where approximately 130 is and shade in the area from 130 to positive infinity, it's all the area to the right of 130, we can use normal CDF, putting in a lower bound of 130, an upper bound of infinity, mean of 100, and a standard deviation of 15. And this comes out to be 0.0228 or 2.28%. So let me just show you on the calculator how that's done. I think you know now, but I'll just go over it just in case. Okay, second, distribution, normal CDF. The lower, we said 130. The upper, E99 for positive infinity. Mean is, mean is 100. Standard deviation is 15. Paste. Okay, and this is a kind of small probability, 0.02275, but that's going to make us, because of the 5 here, we're going to put the 7, make it an 8, so 0.0228. Okay, let's interpret this probability or this proportion. The proportion of people with IQ scores greater than 130 is 2.28%, okay? Which is the same thing as saying the probability of randomly selecting a person with an IQ score greater than 130 is 2.28%. They mean the same thing. Okay, next we're going to look at a few questions that use the normal distribution to estimate a count of people or objects of interest. Once you find the proportion of the population in question, so in this case, the previous example had us find the proportion of a population that had an IQ score more than 130. Once you have that proportion, you can estimate how many individuals in the population this represents, which is a count of people in the population. But in order to do this, you need to know the size of the total population. Okay, you need to know the size of the data set that's normally distributed. Sometimes it will be a population and sometimes it will be a sample. So I wrote that out of order. Sample, lowercase n, or population size, capital N. We have to be provided with that first. And using that total, we can figure out how many individuals satisfy the criteria that we're looking for. Okay, so it can be a sample or population. If we know that it's normally distributed, we can estimate the count. So let's look at a problem where we are provided with a normal distribution and we have to estimate a count. We're going to be using a blood pressure example here. A hospital recorded the systolic blood pressure of 850 patients. Okay, so we have a size here. The results were approximately normal. So that's another way of saying normally distributed. And the mean is 120 and the standard deviation is 10. Now we're not told whether or not 850 is n, lowercase n or capital N, sample or population, but it does not matter to solve this problem. Okay, so in the center of our bell curve, we have the mean and the standard deviation. And the question is going to be, find the number of patients who had systolic blood pressure less than 100. So let's take a look at what that visually looks like on the bell curve. So the problem is not asking us for probability. It's not asking us for proportion, But we are going to get started solving this problem by setting it up in the same way as if it were asking us for probability or proportion. So starting with the bell curve and starting with what we know, the mean and the standard deviation, we can label the horizontal axis. So the center is 120, and for this distribution, we're told that the standard deviation is 10. So let's label three standard deviations above the mean, 130, 140, 150, and three below the mean, 110, 100, and 90. And then let's locate the lower and upper bounds that are in this question. It said we had 100, so we're going to make our vertical line there, and it said less than 100. So try your best. The picture does not have to be perfect, but at least looking at this picture, you can have an understanding of what to expect, what kind of answer to expect. Okay, so let's okay, before I go to the calculator, I want to just identify the size of this either population or sample. We were told that it represents 850 people. So the entire bell curve is 850. If the entire bell curve is 850 and the question is only asking us about this shaded portion, then the size of this shaded portion is clearly going to be something less than 850. But it's not going to be a number between 0 and 1 because I'm not asked to find proportion or probability. I'm asked to find the number of people. That's the question. If everybody is 850, if the entire curve is 850, then how many people are represented in this shaded area here? That's what the question is asking us to solve. So it is not a proportion, that's not the final answer, but the proportion is going to help us solve the problem. So first, let's find the proportion, recognizing that there's more to do after we figure it out, but that's the first step. Let's find the proportion. So we go to the calculator, and since the area that we're trying to figure out the proportion for is area to the left, our lower bound is negative E99, and the upper bound is the blood pressure that was given, 100. So we use the mean and the standard deviation that was provided to us, and we get our proportion, 0.02275. Let's bump that 5 up, that 7 to an 8, and 0.0228. But we don't stop there. We take the answer from step 3, which is calculating the proportion. We take the answer and we just multiply it by 850. So actually, I was incorrect to try to, let me erase that. I didn't want us to round this answer just yet. What I really want us to do is keep the answer as it is and then multiply by 850. So let's do that. Okay, so we're going to take our answer that was just that we got with the proportion and multiply by 850, and we're going to get 19 point something. This number is going to be rounded to the nearest whole number because we're talking about a count of people. So that's when rounded to the nearest whole number, this is 19. So let me take you to the calculator and show you exactly how I did this. Although many of you may know exactly what I did. Just give me a moment. Okay, we're going to do second distribution, normal CDF, area to the left, so negative E 99, 100, and the mean was 120, standard deviation was 10. Okay, so here's our answer, but This is the answer to the proportion. The question asks us how many people does this represent? So we take this proportion and we multiply it by our total. By multiplying it by 850, now we can figure out how many of those 850 people satisfy the criteria of having blood pressure less than 100, and it's only 19 people. So multiply by 850, multiply by your total, and you get your count, 850. Sorry, you get your count, 19 people. Okay, let's interpret this. Out of 850 patients in total, 19 patients have systolic blood pressure less than 100 mmHg. Okay, so 19 patients is our final answer here. Visualizing these results, we shaded in the proportion of area to the left of 100. We figured out what proportion of area that was. We multiplied it by the total, and that gave us 19. So the total is everybody. The total is 100%. In in um in this proportion, the piece of the whole is only about 2%, 2.27, I think. So that came out to be about 19 patients. Let's look at another example using cholesterol. In a study on cholesterol levels, the total cholesterol level of 1,200 adults. So now we have our size. Now, again, we don't know if it's population or sample, but we do have the total, and that's going to become important in the second part of the solution. So we have the cholesterol levels of 1,200 adults. The distribution was approximately normal. The mean 200, standard deviation 20. Okay, so in our center, we have 200 and standard deviation 20. Find the number of adults who had total cholesterol level greater than 230. So this time we're working on the right side of the curve. 230 and greater than 230 is going to shade in the area towards positive infinity. So labeling the horizontal axis, 200 in the center and 20 for a standard deviation. We can do 3 standard deviations on the right and 3 on the left. So 220, 240, 260, and then 180, 160, 140. The lower and upper bounds in question. The lower bound was 230. The question said more than 230, so it's going to go to the right of that, and that's going to take it to an upper bound of positive infinity or positive E99. So let's go to the calculator. Let's figure out what proportion this is. And once we figure out the proportion, we can multiply it by the total, our 1,200. And that's how we'll get our final count. Okay, so lower 230, upper positive infinity, E99, mean 200, standard deviation 20. Get a proportion. You don't have to round this, just take that answer and multiply it by your total. We were provided with a total of 1,200. So we're going to multiply by 1,200. When you hit multiply, it automatically takes the answer prior to it and immediately just multiplies that answer by 1,200. And the final answer, the final count here is 80. Okay, rounding to the nearest whole number, the count is 80. So let's interpret what this means. Out of 1,200 adults, about 80 adults have total cholesterols of more than 230. Okay, so if this number here after the decimal point were 5 or greater, we would round this 80 adults to 81 adults. But we're going to just follow normal rounding rules here. Okay, one more question using estimating counts using heart rate. This time we're told that we have 950 patients. That's our total size in a cardiology clinic, and we were measuring the resting heart rates. Resting heart rate, the heart rates were approximately normally distributed. So that means we can use normal CDF in this problem. The mean is 70 beats per minute, and the standard deviation was 8 beats per minute. So let's consider that the distribution is normally distributed. In the center, we have 70 for the mean. Standard deviation is 8. Find the count or find the number of patients with a resting heart rate between 60 and 80. So it could say find the count, it could say find the number. It's all the same thing. You're finding first the proportion of the bell curve between 60 and 80, and then you multiply by the count. So 60, um, we can estimate the locations of the um, we can label the horizontal axis with the values of heart rate from 70, and then we could go upward, 78. You're adding 8 each time, 86, 94, and then subtract 8, 62, 54, 46. And then between 60 and 80, our lower bound is a little bit to the left of 62. That's a little bit to the left of a z of -1. And our right bound is 80, a little bit to the right of 78. So it's a little bit more than a z-score of +1. And the proportion is the area in between. So let's figure out that proportion on the calculator, normal CDF. So our lower is 60. Our upper is 80. Our mean is 70 given to us. Our standard deviation is 8. Get the proportion and simply press the multiplication key. It's going to bring up that proportion and multiply it by your total, 950. Okay, then you're going to get an answer. We are going to follow normal rounding rules here and just round to the nearest whole number. And we have 749 people. So our interpretation here, out of 950 patients, 749 patients have resting heart rates between 60 and 80 beats per minute. So let me go back to the picture. 749 is our answer. Okay, so looking at this picture, 749 is our answer, the count of the number of people that fall in this range. And 950 was our total. And looking at the picture, it seems reasonable. It seems that this piece of area is a pretty large chunk of the bell curve, a large piece of the bell curve, and therefore it should be a large number like 749 as compared to the total 950. So my answer seems to be reasonable. Okay, so the last thing we're going to do is talk about percentile ranks. So let me go through here. And we're going to look at problems involving percentile ranks. We can use the normal distribution to find a value, the percentile rank for a data value. Okay, so if we look at in this particular distribution, it is normal, and in the center we have the mean of 100. And a standard deviation is 20 here. And you can see this is one standard deviation above the mean, two standard deviations above the mean, three standard deviations above the mean, and on the left, one standard deviation below the mean, two standard deviations below the mean, and three standard deviations below the mean. Below the horizontal axis, you're going to see percentile ranks. So right in the center, where you see the mean, below that mean of 100, you see a percentile rank of 50. And that's what that we discovered when we talked about percentile ranks and the median, that the median is the 50th percentile. It has a percentile rank of 50 because it is halfway through our distribution. 50% of data values fall above the mean, and 50% of data values fall below the mean in a normal distribution. But what you also see are other percentile ranks. For example, there's a percentile rank here of 30. Now that's to the left of 50. The percentile ranks are increasing from left to right. So we have very small percentile ranks on the far left, and as you move to the right, the percentile ranks get bigger and bigger. The percentile rank of 90 is about 30. So here you see where there's 90 and beneath it kind of a little bit to the right, but approximately the percentile rank of 90 is 30. What does that mean? So let's put that into words. What does it mean for the percentile rank of 90 to be 30? And we already did have a discussion on percentiles, so let's review what we know. If the percentile rank of 90 is 30, it means that 30% of the individuals in this data set have values at or below 90. Okay, the percentile rank of 90 is 30. That therefore 30% of individuals have values at or below 90. So you have to be able to make that bridge between the meaning or the percentile rank and its meaning. Okay, so if we think about area now with percentile ranks, if we shade in the values at or below 90, so here's 90, and if we shade at or below 90, if we shade it in, we have a piece of area here, and that piece of area is the percentile rank. It is 30%. So there's a relationship between percentile rank and area. The percentile rank of a number is equal to the area to its left. This is 30%, this shaded in piece right here. And in particular, we call it the bottom 30% because it's on the left side of the curve, the bottom part of the curve, as opposed to things up here are considered the top of the curve. This is the bottom of the curve, the left side. And so the percentile rank of a number is equivalent to the area to its left. The percentile rank of 90 is equivalent to the area to the left of 90, and it is approximately 30%. If we look at other numbers here, looks like, let me pick 110 and 80. We could say that the percentile rank of 110 is 80. And that could mean that 80% of area is to the left of 110. 80% of area is at or below 110. The percentile rank of 110 is 80. So let's do some more examples, and hopefully this tends to set in. Let's look at patient recovery time in terms of percentiles. In a physical therapy clinic, the recovery time for patients after knee surgery follows a normal distribution with a mean of 45 days and a standard deviation of 10 days. Okay, so we have a normally distributed population or group, and we're told the mean and standard deviation. If a patient recovers in 32 days, what is the percentile rank of this recovery time, rounded to the nearest whole number? Okay, so percentile ranks are always expressed as whole numbers. So in order to find that whole number, we'll turn the percent of area into we'll turn the proportion of area into a percent first, and then round to the nearest whole number. So let's make a picture. This is what the distribution of recovery times looks like with average recovery time of 45 days. And in particular, we have a patient who recovered in 32 days. So let's identify where 32 approximately is. If the mean is 45 and the standard deviation is 10, that puts, let's go 45, and then we can go up 55, 65, 75, 3 standard deviations to the right, and down 35, 25, 15, 3 standard deviations to the left. If the particular patient that we're looking at has a recovery time of 32, that puts that patient like over here, a little bit to the left of 35. So we're going to make a vertical line a little bit to the left of 35. And if we're trying to find a percentile rank, the rule is percentile rank measures the percent of area less than that number. So if 32 is the number, the percent of area less than that number is area to the left. So we're going to use our calculator normal CDF to figure out how much of this area do we see here? What's the percent of it? What's that? We're going to express it first as a proportion, then a percent, then we're going to round to the nearest whole number, and that will be the percentile rank. Now, I have an expectation of what it's going to be based on the position of 32. I know percentile ranks go from low to high with values of like 99 up here and values of like 1 and 2 down here. These are low percentile ranks. These are high percentile ranks. And right in the center, I have a percentile rank of 50, right in the center of the bell curve. So since this 32 is on the left of center, I know that the percentile rank has to be a number less than 50. That's the only thing I can really say for certain, but let's see what happens. First, let's find the area in question. This is this shaded in piece. So we're going to go to our calculator, and since the area is being shaded to the left, our lower is negative E99 and our upper is 32. Let me fix that. Okay. And putting that in, we're going to get an answer. And we're going to immediately turn that into a percent. So you can multiply by 100 and turn that 0.0968 into a percent. So multiplying by 100, you're going to get 9.68%. And then rounding to the nearest whole number, because percentile ranks are traditionally rounded to nearest whole numbers, we're going to say that the percentile rank here is 10. So the value was 32. The recovery time in days was 32 days. And being at the 10th percentile, it means that 10% of patients recover in 32 days or less. 10% of patients recover in 32 days or less. So the percentile rank, and I'm going to add here, the percentile rank of 32. Just to realize that, just to emphasize that we're finding the percentile rank for the value 32. The percentile rank of 32 is 10, and that patient, the recovery time 32 is at the 10th percentile, meaning that 10% of patients recover in 32 days or less. Okay, so to recap, first find the area, then multiply by 100, then turn it into the nearest whole number. The area that you're finding is always going to be area to the left. So you're always going to, for percentile ranks. So you're always going to use a negative E99 as your lower bound. Let's do another one with blood pressure. A hospital tracks systolic blood pressure readings for adults and finds they are normally distributed with a mean of 120 and a standard deviation of 15. What is the percentile rank of a patient with a systolic blood pressure of 140? So remember, whenever we see percentile rank and we're asked to find what the percentile rank is, that means we have to find the area to the left of 140. Okay, percentile rank, we're finding the area to the left of the value. So let's label the horizontal axis 120, and 15. Let's do 1, 2, 3 to the right, 130, 150, 165, and to the left, 105, 90, and 75. And the percentile rank for the person with a blood pressure of 140, let's locate where 140 is. And if we're trying to find a percentile rank, we need to know the area to its left. That is the proportion of the population that is less than 140, that has blood pressures less than 140. So finding that area first, multiply by 100, and then turn it into the next whole number, the nearest whole number. So again, it's going to be a lower of negative infinity because we're finding the area to the left, and then an upper of 140, standard deviation 120, and mean of 120, standard deviation of 15, and we get this pretty big proportion. So if I back up and look at this picture, talking about answers that you could expect, looking at my picture, I know because the 50th percentile is in the midway point, the halfway point, that's where the 50th percentile is. I know that 140 is going to have a percentile rank more than 50 because it's on the right side of 50. So it's going to have a higher percentile rank than 50. So when I get 0.90 out of my calculator, it makes sense because I did expect a percentile rank to be greater than 50. So I multiply that by 100 and round it to the nearest whole number. And because it's a 0.87, we're going to round this to 91. So our percentile rank here is 91. Let's interpret what it means. The patient's blood pressure is at the 91st percentile. 91 of patients have blood pressures of 140 or less. Okay. 91% of patients have blood pressures of 140 or less. Okay. The last question we're going to do with percentiles involves comparing two different distributions together. We're going to be comparing heart rate and respiratory rate. So we're going to look at a patient's heart rate and we're going to look at the patient's respiratory rate, and we want to know how the patient ranks in each compared to a typical population. So we have a nurse who's monitoring a patient's heart rate and respiratory rate. For the heart rate, we have a normal distribution, we have the mean, and we have the standard deviation, 70 and 8. And we're told that the patient's heart rate is 79. Okay, without doing any calculations, I know that the percentile rank is going to be more than 50 because the person's mean is, or rather the distribution's mean is 50 and the patient has a heart rate of more than 70. I'm sorry, I said that wrong. The mean is 70. The patient's heart rate is more than 70. Therefore, the patient's percentile rank has to be more than 50. Okay, because 50 is the midway point. and 79 is more than 70. So immediately I have an idea that we're talking about the right side of the distribution. Let's look at the next piece, respiratory rate. Also normally distributed. This time the mean is 16 and the standard deviation is 3. And this patient has a respiratory rate of 21 breaths per minute. Okay, similar to heart rate, the person or the patient has a respiratory rate that is more than the mean. So again, I'm expecting a percentile rank that's more than 50 because 50 is the halfway point. We'll make pictures and we'll show how this is calculated. Which of these measurements is higher in terms of percentile rank? So let's take a look at these two distributions. Um, I've got heart rate over here, and I've got respiratory rate here. And I've got the mean and the standard deviation for each of them. Our patient has a heart rate of 79. Okay, now remember what I said before about the median. The mean, median, and mode all in the center of a normal distribution is 70 here. The median is the 50th percentile, 70 is the 50th percentile. Therefore, anything to the right of 70, anything more than 70 has to have a percentile rank that's greater than 50. And that includes the 79. The other one, for respiratory rate, our patient had a respiratory rate of 21, also more than the standard, also more than the average 16. So since we know that the median is the position of the percentile, has the median percentile rank is 50. We know that anything more than the mean, median, and mode, anything more than 16, 21, has to have a higher percentile rank. So the way we figure these out exactly is by finding the area to the left of the data values. So we're finding the area to the left of 79 in this case. And the area to the left, it turns out to be 0.8697. And we find the area to the left of the respiratory rate of 21. And the area to the left comes out to be 0.9522. So let me just write down how we get this. I'm not going to go to the calculator, but at this point, we've done it a few times. You use normal CDF. Your lower is the left bound, which is negative infinity. Your upper is 79. The mean is 70, and the standard deviation is 8. And the answer comes out to be 0.8697. And on the other side, to figure out the proportion of area, you do, again, the lower is negative E99, the upper, 21. Here the mean is 16 and standard deviation is 3, and the answer comes out to be 0.9522. Now, these are not percentile ranks as they're written. They have to be converted into percents and then rounded to the nearest whole number. So this percentile rank, PR, equals, we're going to take this 0.8697 multiplied by 100, and you get 86.97, and round to the nearest whole number, which makes the percentile rank an 87. And the 21, we get the percentile rank by taking 0.9522 multiplied by 100, 95.22%, round to the nearest whole number, and that gives us 95. So we have a percentile rank of 87 with the case of heart rate and a percentile rank of 95 with the case of respiratory rate. And the one that is higher is the one with the higher percentile rank. That is the respiratory rate. So the percentiles, the patient's respiratory rate is at a higher percentile rank. It's the 95th percentile compared to the heart rate, which is at the 87th percentile. So relative to typical population distributions, the respiratory rate is more elevated than the heart rate. Let me go back to the picture. The respiratory rate is more elevated than the heart rate. So we're using the idea of percentile ranks in this problem to compare two different distributions and make a conclusion. So that is the end of this lecture. I do want to again caution you about the many various ways that the normal distribution can be used to solve problems, and it can get a little confusing. I talked about three ways today: the use of z-scores, the use of using the normal CDF to figure out a count out of the total, and then the third thing was percentile ranks. So that, in addition to the probability questions from last week, are all applications that are solved using normal CDF. So you'll see all those various types of problems on your homework, and with practice, this is not going to become difficult at all. You're going to do just fine, and I will see you at the next lecture.